Definite integrals really are like the meat and potatoes of integrals. Like this is the big idea. It's what helps us find area or accumulation or volume. It helps us solve related rates questions. It's all we're doing is instead of finding an equation that is the integral of something, we're finding something meaningful like the actual accumulation that this graph undergoes from 1 to root 5. Uh, the thing that differentiates this from a indefinite integral is that we have the 1 and the root 5 here, which are the bounds of our interval that we're finding the accumulation of. So this guy is our lower bound, so it's like it's on the left side if we were writing like this is the interval we're finding the area from, like from 1 to root 5. And this is an equivalent thing as putting the 1 on the bottom and the root 5 on the top. So a lot of times people switch them, but you got to be pretty careful not to switch them. How we do these in general is the general rule is that if we take the integral of some function, f of x dx is generally how we write the function, from a to b, well, our answer is just going to be, we're going to take the antiderivative of f, which I'll just call big F of x, and we're going to plug in the bounds, which are a and b. So I'd actually write my answer as big F of b minus big F of a. So this is like the general case. One thing that's lost here that is really important is going to show up later is that you need to make sure you're subtracting everything in f of a. So you need to make sure to use parentheses for that second part. That's where a really large amount of errors come in on these kind of problems. But anyways, let's do some examples. So here, from 1 to root 5 of 3x cubed minus x. So we're going to take the antiderivative, and I'm just going to go straight to this bracket. That's generally how I do it, so I know to plug in 1 and root 5. It's just a notational thing. And the antiderivative is 3/4 x to the 4th, because I raise the power by 1 and divide by the new power. Minus x to the 2 over 2. I no longer have a dx because I have integrated from here to here. And now all I have to do is plug in those points. So I'm going to get 3/4 square root of 5 to the 4th minus the square root of 5 squared over 2 minus, and this is that big point I was talking about where you got to use the big parentheses, minus the 1 plugged in this stuff, which is just going to be 3/4 minus 1/2. 1 plugged in is pretty nice. All right, we can simplify this a little further. 5, okay, root 5 to the 4th is, well, root 5 times root 5 is 5, and we have 2 pairs of those. So this is really like 5 squared, which is 25. So this is really 3 times 25 over 4. Minus, well, root 5 squared I said was 5. Yeah, it's 5. So 5/2. We have a minus 3/4, and we have a plus 1/2. I should probably get common denominators here. 75 over 4 minus 10 over 4 minus 3 over 4 plus 2 over 4. So 75 minus 10 is 65, 62, 64. So I actually get 64 over 4, which I know is 16. So that's kind of another big idea about this section, is you don't get an equation as your answer, you get a number. In this case, a pretty nice number, which was somewhat unexpected with the 1 and root 5. And this number indicates the accumulation under the graph, so like the area under the graph, the absolute value of the area under the graph, from 1 to root 5 of this function. So let's move on to our next problem here. This one has an easier integral. So I'm going to go straight to the bracket. This is one where we got to think about kind of like the reverse chain rule here. The thing that gives me sine is a negative cosine. So I'm going to have a negative cosine of 4x. But I have to think about the fact that I'd be multiplying by 4 if I took the derivative of this because of the chain rule. So I got to divide by 4 in my integral. Alright, now I'm just going to plug in values. I get negative cosine of 4 pi over 8 over 4 minus a negative cosine of 0 pi over 8, or 0 times 4 is just 0 rather, over 4. So cosine is of 4 pi over 8 is cosine of pi over 2. Cosine of pi over 2 is at the top of our unit circle at 0. So this is really 0 plus, because minus a negative, 1 over 4. And so the answer is just a fourth. Another one with a pretty nice answer. Let's see if our streak continues. We're integrating from 0 to 1 of 2 over x plus 1. I'm going to rewrite this real quick as integrating from 0 to 1 of 2 times x plus 1 to the negative 1 power. Okay, now I'm just going to pull down the power and subtract 1 from the power. And I'm going to get negative 2, because negative 1 times 2 is that, times x plus 1 to the negative 2. Cool. Now I'm just going to plug in my bounds, which are 1 and 0. If I plug in 1, I get negative 2 times 2 to the negative 2. And if I plug in 1, or 0 rather, I get negative 2 times 1 to the negative 2. So realistically here, I have this is negative 2 over 2 squared, so it's negative 2 over 4. And this is minus a negative, so plus 2 times, well, 2 divided by 1 squared, so that's 2. So really this is just negative 1/2 plus 2, which is 3/2. If you're getting to this step, or getting to this step and not getting the correct answer, the most likely cause is difficulty adding fractions or combining fractions or converting powers. This section is really heavily involved with adding and subtracting fractions to get the right answer. You just have to get better at it in order to get to the answer, and you're going to get a ton of practice because every time we do a definite integral, you got to plug in stuff, and very often, because we have power functions that divide by things, like over here, we have a power function without any fractions, but when we take the integral, we do have fractions. We're just going to have a ton of fractions problems. All right, that's it for this section.